In the previous video lecture, we have seen about 8255 and how we can interface this 8255 IC with the processors. So in this video lecture, we are going to see about the analog to digital converter. So what is this analog to digital converter? So this is nothing but an IC which converts an analog signal into a digital signal. So digital signals are nothing but zeros and ones. So it converts the analog signal into a digital data. So what's the need for this analog to digital converter? So what's the need in the sense? So in the real world, the signal that we get are in the form of analog signals. Okay, fine. So but the process that we have in the real time, that's nothing but 8085 that we have seen, 8086, the latest process till now. They have released this Intel i7, i5, all these processors and controllers are able to process only the digital data and not the analog data. So it can't understand the values of the analog signal. So in that case, we are supposed to convert these analog signals into a digital signal. In that case, we are supposed to use the ICs like these analog to digital converters to convert the analog signal into a digital signal. Fine. The processors does not have this kind of peripherals inside. So we are supposed to connect these kind of ICs as an external device to perform these operations. But in case of controllers, we have these peripherals inside the IC itself. Okay, so inside the controller IC, we are having a central processing unit as well as these kind of peripherals, this analog to digital converters. So that we can straightly connect the analog signal with these controllers. So it will convert the analog signal into a digital signal and it continues with its process. So but here in case of processors, we are supposed to interface these analog to digital converters as an external device with the processor ICs. So we can't straight away connect this analog to digital converter with the processors. So we are supposed to use an interconnect IC called as 8255. So this we have seen in the previous video lecture. So 8255 is nothing but programmable input output device. So we are supposed to use this IC as an interface device between the processor and the analog to digital converter. So in this video lecture, we are going to see about why we are going for analog to digital converter, the types, and in specific we are going to see about the analog to digital converter IC 800808, so which adapts to a specific type of conversion called a successive approximation type. We are not going to see in depth about the conversion. We are going to see how this IC works and how we can interface this 0808 IC with 85 or 86 microprocessor. Fine. So first we will see the purpose of it. So as I have already told you, the real time signals are of in the analog form. We can't process as it is. So we are converting that analog signal into a digital signal. Okay. So here I have taken an example that you are going to process the audio signal. Okay. So the audio signal you will get from the microphone as an input. Through mic you are speaking something, so that's an audio signal. So these audio signals are to be processed by the digital signal processor. So these kind of processor does not take the analog signals as such. Okay, the analog signals would be like this. Okay, so we are supposed to use an analog to digital converter in between your input device and then the processor. This will convert your analog signal into digital data like this. Okay, so the processor then it will process and gives the output as this only. So like the digital data only it will give the output, but in the real world you can't take the digital data as such. We can't understand the details of these data. So we are supposed to use again a digital to analog converter. So that it will convert these digital data into analog data that we will give to the speaker so that we can get an audio signal. So as it has recorded in the microphone. Okay. So as an input device you are supposed to use analog to digital converter. For the output device you are supposed to use digital to analog converter. So in this video lecture we are going to see about this part, analog to digital converter. So as I have already told you, we can straight away connect this processor with the analog to digital converter. So we are supposed to use an 8255 as an intermediate device. Fine. So consider this as your processor. This is your processor ID, either it can be 85 or 86, and this is your analog to digital converter, and here you have your input device. So this input device will give analog signal. Okay, so this analog signal is not understandable by the processor, so you are using the converter called as digital to analog converter that will convert these digital signals into zeros and ones. Okay, so this signal, digital converter, we can't straight away connect with the processor, so we are supposed to use 8255 IC. Fine. So this digital data is given to the processor through 8255. So now this analog to digital converter is input for this processor. Okay, so we are supposed to use IO configuration. IO configuration in the sense we have seen in the first unit IO interfacing logics. Yes, so we are supposed to use that logic here for connecting with this 8255 analog to digital converter with the processor, and you are supposed to use in and out instruction to communicate with this device. Fine. So these will see how to, so this we will see how to convert, how to program, how we can, what are the steps we can follow for this and all later. Okay, so as I have told you, this analog to digital converter is an input device for the processor. Okay, so this analog to digital converter will start to convert these analog data into digital data only if it gets start of conversion signal. Okay, this signal is nothing but SOC, start of conversion. Okay, so again I will draw your processor 8255 and then your analog to digital converter. Okay, this converter will start to convert only it gets the SOC signal, which is nothing but start of conversion. So this is nothing but a pulse. Okay, a digital pulse for a quite duration. Okay, so this signal is issued by the processor. So this processor will issue the start of conversion so that these analog to digital converter will start to convert this analog data into a digital data. So once this conversion is over, okay, once this analog signal is completely converted into a digital signal, so the processor so this analog to digital converter device will issue a signal to the processor to indicate the end of this conversion. So that signal is called as an EOC, end of conversion. Okay, EOC. So this signal is issued by the analog to digital converter to the processor to indicate that the conversion is over. Fine. Okay, so the next thing is conversion delay. So this conversion delay is an important term here. The conversion delay is an important term while we consider the analog to digital converter. So this is nothing but the time taken by the converter to convert or to complete its conversion from analog to digital data. Okay, so this is nothing but it's to say it simply, the time it takes to convert the analog data is called as conversion delay. So if we want to say more technically in the sense, the time when the start of conversion is issued. So consider this as your start of conversion. The time when the active edge of start of conversion till the active edge of, this is the active edge of end of conversion is known as conversion delay, which means, so this time is known as conversion delay. So this would be the technical definition, and more simply if we would say that the time taken by the converter to complete its conversion from analog to digital data is known as conversion delay. Fine. Okay. Okay, next we will see the types of ADC. The types of ADCs are single slope ADC, dual slope ADC, successive approximation, and last one is flash time. Okay. So how these ADCs are differing in the sense how fast they are converting these analog to digital data. So based on this, these types are categorized. Okay. So this single slope and dual slope are slow conversion Okay, this will perform a slow conversion, but it having more accuracy than other converters. So this flash type is more faster, okay, more faster than all these things, but accuracy is low. Accuracy is very low here. So these two converters are having more accuracy, but this is having less accuracy. This successive approximation is having medium speed, okay, and accuracy is also considerable, but the thing is, then single and dual slope, this accuracy is low. Compared to single and dual, its accuracy is low, but when you compare with flash type, its accuracy is high, but it's having medium speed. Fine. So in most of the applications, successive approximation only used. Fine. So I'm not going in depth how this successive approximation is happening, how this conversion happen. So we are not going to touch in that topic. We are going to see only the analog to digital converter IC that we are going to see. Fine. So that how the conversion is happening, how we can interface that with the processor. Okay. Before we see to the particular analog to digital converter IC, we will see how the algorithm of analog to digital converter. Okay. So the first step in conversion is that you are supposed to ensure the stability of the analog signal. So what this step means in the sense, so you are having an analog signal which varies respect to the time, right? So if it varies very fastly, the converter cannot convert to that time fast that the input signal is, okay? So you are having an analog signal like this. So if this is varying continuously with respect to time, okay? So if it varies continuously, that means fastly, the converter cannot match to this fast and convert to a digital signal, because the converter, the analog to digital converter will take some time to convert a single time period. That means at a particular, for example, if you are having an voltage level of 2 volt at the time period 2 microsecond, okay, to convert the 2 volt at 2 microsecond, it will take some time. So for that period of time, that 2 volt should be maintained, or it should not be varied for some time period, so that we can get the accurate value. Okay, if it varies during the conversion process is happening, if it varies from 2 volt to 3 volt, when the conversion is happening, obviously you won't get the correct data, correct digital data as an output. Okay, so the first thing, you are supposed to ensure the stability of the input signal. So for some time period, your input signal should be maintained in the same voltage level, so that the conversion happens smoothly. So this ensuring is done by the sample and hold circuit. Okay, so most of the analog to digital converters will have such circuit, sample and hold circuit internally, so that it ensures the stability of the input signal. So I'm not going to say how this sample and hold circuit works. Okay, so I'm just saying that this circuit is used to ensure the stability. Fine. And the second step, first step is to ensure the stability, and second step is to issue the startup conversion signal. Okay, so this would be like a pulse that I have already told you. This signal is issued by the processor. Okay, so when the analog to digital converter sees to this, when the analog to digital converter see to this SOC signal, it will start up with the conversion. Fine. And then the third algorithm, then the third step is that read the end of conversion. Okay, so this signal end of conversion will be issued by the analog to digital converter to microprocessor to indicate that the conversion has been ended. Fine. So that's the third step. And the fourth step, we can read the digital data from the analog to digital converter. Fine. So these are the 4 steps of analog to digital converter. Fine. So in this syllabus, in your syllabus, we are going to see about the IC0808, which is nothing but an analog to digital converter. Now we are going to see how its block diagram is, the pin diagram of 0808, how we can interface this device, this analog to digital converter with 8086 microprocessor. Fine. Okay, so first we will see that it's an 8-bit CMOS IC. So 8-bit, what this 8-bit represents in the sense, the output, the digital output. Fine, ADC will have a digital output, no? So this digital output is of 8-bit. Okay, so if you give a 5 volt input signal to this analog to digital converter, this will represent this 5 volt into its corresponding digital data in 8-bit format. Okay, in 8-bit format. Okay, so this is what it represents. So the output bit capacity is represented by this. So 8-bit CMOS device which adapts to successive approximation method. Fine. So it's an faster one, as I have already told you, compared to the other device, and the conversion delay of this IC is 10 microseconds at a clock frequency of 40 kilohertz. Okay, so the conversion delay, as I have already told you, is nothing but time taken by the device to convert an analog data into a digital data. Fine. So the next important thing is it's having 3:8 multiplexer. Okay, so if you see to the block diagram, so this is the block diagram of analog to digital converter. Okay, if you see to this, you are having an multiplexer which is of 3:8. So it is having 3 select signals and 8 input signals, which is nothing but you can give 8 analog inputs. Okay, you can connect 8 analog inputs, which is nothing but 8 devices, 8 different devices, which gives the analog data as an input. Okay, so this mux will select either of these 8 inputs. Okay, so using the select lines, it will select either of these 8 inputs. Fine. Okay, so this is what mentioned here using the select lines. Okay, A, B, C. Okay, and the next thing is it's an unipolar ADC. So unipolar ADC, in the sense, it will be able to convert only the positive signal and not the negative signal. Okay, so it will be able to convert only the positive 5 volt, the negative 5 volt it won't consider. So it does not have that capacity to convert the negative voltage into a corresponding digital data. So that's called as unipolar ADC. And the next important thing is that this IC 0808 does not have the sample and hold circuit inside it. So if you want to use this IC, you have to design an analog, you are supposed to design your own sample and hold circuit, and you have to connect it externally with this converter, so that you can ensure the stability of the input signal. Fine. So this is what the block diagram of analog to digital converter 0808. You are having 3:8 multiplexer, SA nothing but successive approximation register, then this is nothing but a DAC, digital to analog converter, then the output latch. Fine. Okay, so based on the select signals A, D, C, either of the 8 inputs will be selected. So this will be given to the comparator. What this comparator will do is, okay, so here you will have an analog data. Okay, so this comparator will compare the analog data from the DAC that we have given here. Fine. So based on this comparison, if your output voltage of DAC is greater than the input voltage, okay, either of these input voltage, you will get 1. If it is less than, means you will get 0. So based on this 1 and 0, here the digital value will be decided. Okay, so this conversion will happen only when the start of conversion is issued by the processor. Okay, if you get the start of conversion, the comparator will start to compare the input voltage and the output of this VDAC. Okay, based on this, 0 or 1 will be issued to the SAR. The SAR will decide the digital data. Fine. So after that, till then you get the end of conversion, this conversion will happen. Okay. So once this first conversion is over, again your reference voltage will be divided by 2, then by 4, then by 8. Okay, this will continue till the end of conversion has happened, which means that till the 8 bits got converted. Okay, so after the conversion, this 8-bit data will be stored here in the output latch. So from the output latch, the processor will get the digital data. Okay, so this is how the conversion will happen here in 0808. So this is the pin diagram of that. Here you have your ground, V reference, VCC, this you all know. Okay, these are all the 8 input lines, and these 3 are the select lines. Okay, your address latch enable, and these are all the output lines. Negative reference, which is nothing but ground. So these are all the output, your start of conversion, end of conversion, and Y is nothing but output enable. So this output enable should be high. Okay, it should be high so that you will get the output from this output latch. If it is low, you cannot take the value from the output latch. Fine. So this is what the configuration for selecting the input signals. So if your select lines A, B, C is 0, 0, your input 0 line will be selected. If it is 1, 0, 0, input 4 will be selected. If it is 1, 1, 0, 6 will be selected. So this is what the configuration for that. Based on the select lines, our input signals will be selected. Okay, next we will see an example for interfacing this 0808 with 8086 microprocessor. Fine. So here I have taken an example from the book A.K. Roy. You can see that in that also. Okay, fine. In that example, they are interfacing this 8086 with the ADC through 8255. Fine. So what they have given is, so they have taken an analog input IP2. Okay. So to select the IP2, your ADC, sorry, your ABC, the select lines. Okay. So IP2 should be selected. So your A, B, C should be configured in a such a way your IP2 will be selected. Okay, you are supposed to convert the analog input from this. So in the example they have given, you are giving input 2 through IP2 pin should be selected. So it should be selected in such a way that these values should be configured to a value so that this input will be selected. Fine. And they are saying that the output enable and the ALE should be given with 5 volt. It should be high so that we can get the output from the output latch. Okay, and they are also saying that port A of 8255. So this ports represents 8255. So from 8255, your outputs are connected, which is nothing but these lines are connected with port A. So your output O0 to O7 is given to port A as of here, and they are saying port C upper act as an input port to receive the end of conversion. Okay, so port C upper, which is nothing but PC7, is given with end of conversion. So this is an input for processor. Fine. And then port C lower, which is nothing but PC0, which is given as startup conversion, which is output for processor, because startup conversion is issued by the processor. So it's output for processor. So in port A, you are getting the 8-bit digital data. Okay, this is input for microprocessor. Fine. And then port B, you are collecting the select lines B, C, A, B, C. Okay. So this is what here. So these ports, port A, C7, C0, port B are from 8255. Okay. So and these things are belongs to ADC. Okay. So what you have to do now, you are supposed to configure these ports, port A, port C and port B in such a way you are supposed to have this configuration. Fine. So how we can configure these ports? Do you all remember? Yes, we are supposed to use the control word register to configure these ports as an input or output. So that we will see now. So what's the thing? You are supposed to use all these ports are used in the mode of IO, right? So in IO basic mode only these things are used. Okay. So for that, what will be the value? D7, D6 are to be 1. So 1 in the sense IO mode is selected, right? So on D6, D5, see here D6, D5 are meant to select the mode of group A. So what mode you are using? Basic mode. Basic mode belongs to mode 0. So these values should be 0, 0. So then D4 is belongs to port A. So port A, how you are using? You are using as an input. So if you are supposed to use as an input, you have to give 1. So we have given 1. So D3. So D3 is meant for port C upper. So port C upper, you are connecting end of conversion. This is also an input. So you are supposed to give 1. So then D2. So D2 decides the mode of port B. So port B, this is also you are using in mode 0. So you are supposed to give 0 value here. So then D1. So this will decide whether port B is input or output. So port B, what we are using here, you are using as an output because it's a select line, no? So you are giving 0. So D0 is to select port C lower. Port C lower also you are using as an output. So 0 is here. So as a total, you are getting a 98 as an hexadecimal value. So this 98 you have to give to the 8255 control board register to configure these ports. Fine. So this is of this interfacing will there. Okay. So consider you are having your processor here. Okay. So this is your 8255 IC and this is your analog to digital converter. Fine. As I have already told you, this device is having an mux inside. 3:1 mux that will select the input. Okay. So based on the select lines B, C, A, B, C, IP2 will be selected. So these A, B, C are connected with port B. Okay. So that's why port B are configured as an output. So port P0, B1, B2 are connected with A, B, C respectively. Your output enable and ALE are connected with positive 5 volt. Okay. So based on this, your IP2 will be selected, grounded. V reference is also grounded, negative V reference. Fine. Positive V reference is given with positive 5 volt. So this reference is for DAG. Okay. Don't get confused. And this VCC is for to operate this IC. 0808 has to operate. No. So for that this 5 volt is given. So this 5 volt is given as a reference for the digital to analog converter that is inside here. And then a clock signal is also given. Okay. So the start of conversion is issued by PC0. The end of conversion is issued by the ADC that is connected with PC7. Okay. So then the output of the digital to analog converter is given to port A. So this port A is connected with this data lines. Okay. So these A2 and A1 line are connected with 1 and 0 to select the ports and registers. And then reset pin, IO read, IO write signals are connected in this way. Fine. So this is how a connection will be. So now we will see a simple program to operate this analog to digital converter using the processor 8086. So this program is for this example. Fine. So the first thing you are supposed to configure 8255. So that's why you are given a value 98 to AL register. Okay. So as I have already told you, these devices are input and output devices. So you are performing an IO interfacing so that you are supposed to use only in and out instruction. So in instruction means the processor will receive data, out instruction means the processor is giving the data to the peripheral device. Fine. So these in and out instruction or in and out, that means sending a data, receiving a data should be happen through the accumulator register. So the accumulator register here is AX register which is of 16-bit. Fine. So since we are dealing with 8-bit data, the AL register, lower bit of AX register is used here. Fine. Okay. So that's why we have used AL register here. So this 98 is nothing but configuration value. Okay, that is given to AL register. So from AL it is given to CWR, which is nothing but control word register of 8255 using out instruction. You are giving data from 8086. You are configuring this 8255. So now we are configured, and then you are supposed to select the input channel IP2, right? So for that your C, B, A value should be 0, 1, 0. So its equivalent value is 0, 2. So that is given here. So from AL it is given to port B to select the input signal here. So here configuration is over. Here we have selected the input. Next we are supposed to give the start of conversion. So the start of conversion is low to high pulse. It should be retained for some time period. So this start of conversion is issued by PC0. Okay. So PC0, you are supposed to pass this value to port C then. Okay. So first 0, 0 is given, then 0, 1 is given, then 0, 0 is given, because this high signal should be retained for some time period, then it should get low. Okay. So that's what happened here. First low signal is given, then high 0, 1 is given, then low signal is given. Now the start of conversion is issued. Okay. So once the start of conversion is issued, the analog to digital converter will start its conversion. So now it will start to convert this analog data into 8-bit digital data. Okay. So next what we have to do, we have configured, we have selected the input, we have done with start of conversion. Now the conversion is happening. Once the conversion is, you are supposed to issue the end of conversion, right? So start of conversion is given, immediately the start of conversion is given, your analog to digital converter will proceed with the conversion. Once it's converted the analog data into an 8-bit digital data, which means the conversion is over. So now your digital converter should say the process that the conversion is over, now you can get the data from the device. Okay, so that has to be signaled, no? So that is signaled by using the end of conversion. So this is issued by the analog to digital converter to the processor, right? So now processor, what it has to do, it should check whether the end of conversion has been received or not. So where it will check? So we have connected that end of conversion with PC7. Do you remember the previous circuit we have seen? So this end of conversion is connected with PC7. So now the processor, so this PC7 is input for microprocessor. So the processor now it will check in AL comma port C. So first it will get the value from port C. Okay, so then it will check whether this bit is 1 or not. So how it is checking PC7 is 1 or not, in the sense, so it is rotating the value from port C. Okay, RLC in the sense rotate left through carry. Okay, so if this is your 8-bit signal and this is your carry, so now what it will do is it will rotate the signal like this. So for example, if the 7th bit is 1, now when you are rotating, your carry will also become 1. So at that time, the next what you will do is jump on no carry. It will check whether carry is 1 or not. If the carry is 1, which means that end of conversion is issued. So now once the end of conversion is issued, what it will do? We can read the data from the output latch or through the port A, because the output value is connected with port A, remember? So we can read the data from port A. Or else, if this end of conversion, that is carry, is 0, which means that the end of conversion is not received yet. Fine. So which means that the conversion is happening still. So again, what the processor have to do, the carry will not occur there, again it will go on to the loop. What it will do, again it will go on to the loop and will check whether the port A receive the signal, rotate it, check the carry has been occurred or not. So this process will happen until your 7th bit PC7 is 1 or not. 1 in the sense end of conversion is occurred. If not, the conversion is not yet finished. Fine. So this loop will happen until PC7 is 1. So if the PC7 is 1, when you rotate, the carry will become 1. So which indicates end of conversion has been occurred. So once the end of conversion is over, the data will be available on the port output latch. Remember? So you had a block, right? So in the output latch, you will have your data. So from the output latch, it will be given to port A. From port A, your processor will receive it. Okay, you are supposed to use in instruction. IN AL comma port A. So from port A your processor will read the digital data. Fine. So this is how we are supposed to frame a program. So first you have to configure your 8255. Why? In the sense, since you are connecting your ADC through 8255 with the processor. Okay, so that the connection will become easier, and you are supposed to configure this 8255. So first you have to configure your control word register. Second thing, you are select your input. Third, you are supposed to issue the startup conversion. Again, fourth step, you have to check for the end of conversion. If the end of conversion is issued, you can take the data from the port A.